everyone. I'm Sujani, Faculty in Physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to start the fourth module in the course Engineering Physics, and that is Light and Optics. Let us look at the brief outline of this module. First, we are going to discuss about the Huygens principle, then the superposition of waves. Then we are going to discuss about the Young's double slit experiment and then derive the expression for fringe width. We are also going to see the Newton's rings experiment and derive expressions for the radius of curvature and the wavelength. Then we will discuss about the Fraunhofer diffraction due to a single slit, then double slit, and then finally we'll discuss about diffraction grating, that is due to N slits. So the topic for today's discussion is Huygens principle and superposition of waves. So let us look at how we are going to discuss this topic. First, we will see the brief history of wave theory, and then we will try to understand the principle that is given by Huygens to construct the wavefront. So we will try to see how to construct the wavefront. Then we'll discuss the principle of superposition. After that, we have interference, and in interference we have two types, constructive and destructive. So first, coming to the history. Light always attracted the curiosity of thinkers and scientists. And in the late 17th century, scientists were embroiled in a debate about the fundamental nature of light, whether it is a wave or a particle. And then they began to comprehend the properties of light. And as we all know, Sir Isaac Newton was a strong advocate of particle nature of light. So Newton always believed that light traveled in the form of particles. And then this scientist, the Dutch physicist Christian Huygens, he believed that light was made up of waves that are vibrating up and down perpendicular to the direction of wave propagation. And he also formulated a way of visualizing the wave propagation. Then in 1678, another scientist by name Huygens, he proposed that every point that a luminous disturbance meets turns into a source of the spherical wave itself. We are going to discuss in detail about this luminous disturbance, how it meets a point and then how it becomes a source. Then the sum of the secondary sources, which are the result of the primary disturbance, determines what the new wave is going to be like. And this theory of light is known as the Huygens principle. Huygens, with his theory, he was successful in deriving the laws of reflection and refraction with the theory that he proposed. That means when any luminescence strikes a point and that point acts as a secondary source and it emits waves. And with the help of that, he could clearly explain the laws of reflection as well as refraction. Reflection here means whenever light falls on a surface, a reflecting surface which do not transmit the light, it reflects back into the same medium. Suppose this is the surface, a polished surface we take, and light is incident on this. So when light strikes this surface here, it is reflected back into the same medium. So with the help of this principle, he could easily explain this, and he also could prove the laws of reflection. What is the main law of reflection? The angle of incidence should always be equal to the angle of reflection. And also they lie in the same medium. Okay, all these things he could successfully explain. Then coming to refraction, this is about reflection. And then when it comes to refraction, it is all about the bending of the light ray at the surface of separation of two different media. Means if you have a media through which light can transmit, we have one media, air, suppose, and this is glass. A ray of light is incident on the surface. If this is the normal. So when this ray goes from one medium to another medium at the surface, this is the surface of separation of the two media, this ray will bend. This is I, this is R. And in this case, what we are seeing here is the ray of light bends towards the normal because it comes from a rarer medium to a denser medium. Now, when the ray comes from a denser medium to a rarer medium, suppose you take glass and you take air. If this is the normal, if a ray of light is incident, this is the angle of incidence. Now, even in this case, the light ray bends at the surface of separation of the two different media, but here it bends away from the normal. So this is going to be R. So this is the main law of refraction. So Huygens with his principle could explain these laws of reflection as well as refraction. He was also successful in explaining the linear as well as the spherical propagation of light. So when light is propagating forward in a medium, if it is going in a linear way, how do we explain it? And if it has got spherical propagation, he could also explain it with the help of this theory. But the only constraint was he was not able to explain the diffraction effects of light. So diffraction here represents the bending of the light around the corners of the obstacle. So this is related to bending of light. In refraction, we have seen bending of light at the surface of separation. But here we are talking about the bending of light around the corners of an obstacle. And also here in diffraction, we see that the size of the obstacles should be very small, that is comparable with the wavelength of light. So he was not able to explain this particular phenomena or property of light, that is diffraction, with the help of his theory. Now, whenever we talk about a theory, if you are putting forward a theory, you should be able to give the mathematical representation for that and also an experiment to support or prove what we are claiming. So, in the year 1803, the experiment was conducted by Thomas Young on the interference of light, and that proved the Huygens wave theory. So, this scientist, when he was experimenting on interference of light, so with the help of this, what he could explain is whatever theory that was put forward by Huygens, it was correct. And another scientist in the year 1815 by name Fresnel, he provided the mathematical representations for the Young's experiment. Whatever Young showed in his experiment, he could give the mathematical equations for it. So this proof by Fresnel and also the experimental evidence by Thomas Young supported the Huygens theory very well. Now, if you see the theory of light, Max Planck proposed that light is made up of fine packets of energy known as light quantum, and it depends upon the frequency and the velocity of light. And in the year 1905, Einstein proposed that light possessed both particle as well as wave nature. He suggested that light is made up of small particles called photons. So what Einstein proposed is whenever light is incident on a surface, it is incident in the form of photons. And a photon is nothing but a small packet of energy. And quantum mechanics gave proof for the dual nature of light. Dual nature here, when we are talking about, it is wave as well as particle. So they finally agreed that light has both wave as well as particle nature. Under certain circumstances, to explain certain phenomena, we use the wave nature of light, and to explain the other phenomena, we use the particle nature of light. Now, when it comes to a wave, in general, any type of wave you will see, a wave is formed due to a disturbance that is caused in medium. So, whenever there is a disturbance in a medium, a wave propagates forward. The best example you can see here is whenever we drop a stone in water. So, you see ripples of water. So, here you see in the figure, suppose a stone is dropped at this position. So, you will have ripples, or we call them as waves, that are propagating in all the directions. So, this is how we have the waves. A wave is nothing but a propagation of energy. Now, I will put it in simple words, whatever principle that was given by Huygen. So, he proposed that every point on the wavefront acts as a source for secondary waves. So, suppose you have a wave, every point on the wave will act as a source and it will start emitting secondary waves. We are going to see and construct a secondary wave. So, let us now try to draw the wave. So, consider a point source of sound. So, we'll consider a point source like this. Means, suppose if you are dropping a stone in water, this is the position at which we are dropping. So, in step 1, what we are going to do is, we will draw a spherical wave around the sound source. So, this is the point. So, around this we are drawing a spherical wave. So, this is a spherical wave around this, means with this point as the center. Okay, using a compass, you can draw a circle of convenient radius that becomes the wavefront. I can say this is the initial wavefront. Now in step 2, what we are going to do is draw a few equally spaced points. Here they are represented by the blue dots on the circular wavefront. Means this is the point of disturbance. And this is the wavefront, spherical wavefront we have drawn with this as the center. Now what we are going to do is we are going to mark some equally spaced points on the circular wavefront. Then in step 3, we will draw arcs of circles around each point of the wavefront. So, whatever points we have considered here, these are the points we have considered on the primary wavefront. This is the point of disturbance. This is the initial wavefront. So, with each point as a center, taking a convenient radius, we are going to draw arcs. With the same radius, keep it here, keep the compass here, again draw an arc. So, from each point, we keep on drawing arcs. So, this is how we draw the arcs. Now, in step 4, you draw a curve that is a tangent to the individual circular wavefronts. So, this is a wavefront now. This is one. This is one. We have many wavefronts. Now, what we are going to do is, we are going to draw a tangent. Means a curve that touches these lines at one particular point or at normal to this wavefront. So when you draw tangent, you get a new wavefront. So when we are joining all these with the help of a tangent, you get the new wavefront. So what we see here is this is the point of disturbance. This is the primary wavefront. So we are talking about the construction of a wavefront. We have the point source and this is the primary wavefront. Considering different points on the primary wavefront, we have drawn arcs. These are the arcs. And finally, we have drawn a tangent to these arcs, which gives us the new wavefront. Or we call it as a secondary wavefront. So according to Huygen, what he is saying is every point on the wavefront acts as a secondary source. Now, these are the points on the wavefront and these points are now acting as secondary sources, and with the help of these sources, we are constructing a new wavefront. So we get the new wavefront. Now, plane waves can also be created if we are having a rectangular slit. So how do we get plane waves? Is if you imagine that dropping a stick in a pond. So instead of dropping a pebble, if you are dropping a pebble, we have seen you will have circular wavefronts or a spherical wavefront. But when you are taking a stick and drop it in water, then what you see is plane waves that are propagating forward. So we can also draw these plane wavefronts using the Huygens principle. In the same way, we have drawn spherical wavefronts. So what we are going to see here is, this is the wavefront, incident wavefront. So on the incident wavefront, you are going to consider different points on the wavefront. Now these points will act as secondary sources. So now with each point as a center and the same radius, you start drawing circles with the same radius. So when you are drawing circles, so you will get circles like this. These will be the sources now, secondary sources. Now what we are going to do is you draw a tangent to all these circles. So this tangent which is drawn will give us the new wavefront. This is the new wavefront. This is how we are going to draw a plane wavefront. So the same way, if you are doing in one direction along the positive x-axis, this can also be done on the other side, that is the negative axis. So when you are drawing a line joining the arcs on the negative side, you will have a wavefront on. So you will be seeing if these are the secondary sources. So you will have the propagation in both the direction along the positive x-axis as well as the negative x-axis. And then we can continue to draw more waves onto the right. Now what happens? These points will become again the sources, and with the help of these again you can draw circles and then draw a tangent touching the circles that gives the new wavefront. So in the same way you can keep on continuing. So as the wave propagates, it remains as a plane wave. So the plane wave is represented by these black lines. Now here we are discussing about three different choices. The first one, if the slit or the point of disturbance is a point, okay, then we have spherical wavefronts like this. We'll be drawing arcs like this and the wave keeps on propagating forward. Now if you imagine that the width of the slit is big, if it is not a point source, if it is big, then what happens? You will have wavefronts like this slightly cylindrical in shape. So the wave propagates in this fashion. Here we are calling it as spherical. This is a spherical wavefront. This is a cylindrical. And now the third one we have seen is if the disturbance is a plane wave, then we'll get a plane wavefront. This is a plane wavefront. Now we are going to see all points on the wavefront acts as new sources for the production of spherical secondary waves. So we have taken a wavefront. We have taken points on the wavefront. This is the old wavefront. On the old wavefront, we have taken points. And with these points, we have drawn the arcs. And we have drawn a tangent to these arcs. And this gives us the new wavefront. The same thing we have seen with spherical also. This is the old wavefront. This is the old wavefront. On the old wavefront, we have taken points. So, as given by Huygen, what he says is, all these points on the wavefront will now act as secondary sources and they will start emitting waves. So, that is how the wave propagates forward. So, if these are the points, we are drawing arcs like this. And the tangent drawn to all these arcs is giving us the new wavefront. This is all about Huygens principle. Now coming to the principle of superposition. When two waves arrive at a point simultaneously means at the same time, they superimpose on each other and the amplitude of the resultant wave is the vector sum of individual amplitudes. So we need to understand certain terms here. First thing is the amplitude, and then we will also understand what is the vector sum. So when I talk about a wave, this is a wave. For example, this is the origin. Along the x-axis it propagates. This is the displacement. The maximum displacement, we call it as amplitude. Amplitude is nothing but the maximum displacement from its mean position. So, here amplitude is shown by A. So, when there are two waves that are arriving at a point simultaneously at the same time, so the amplitude of the resultant wave is the vector sum of the two individual amplitudes. Why we have to take the vector sum? Because when we talk about vector sum, we also consider the direction in which the waves are reaching. Suppose I have a point P here. So there are two waves that are coming and reaching at this point in the same direction. Or in another case, I may have the waves. This is coming in this direction and the other one is coming in this direction. So if the displacement of this is y1 and the displacement of this is y2. So the resultant will be the vector sum of the two displacements here. If I take y1, that is in the positive x direction, as plus y1, the one which is going in the negative direction, I'll take it as minus y2. So the resultant displacement is the vector sum of the two. Now here we see the example. Two waves passing through the same region will superimpose and their displacements will simply add. Simply add means it is a vector sum. So while passing, the displacement is the sum of the individual displacements. So we are talking about the first wave going along the positive x direction and the displacement is given by y1 for this wave. And we are considering a second wave whose displacement is given by y2. And you imagine that these two waves superimpose on each other. They are arriving at the same point at the same time. Then what happens? There is superimposition. So when they superimpose, what will be the resultant wave? So the resultant wave y is given by the vector sum of the two waves, that is y1 plus y2. So this is our first wave which is getting modified because it is the vector sum due to the second wave, which is our second wave. This dotted line represents the second wave. So this will be the final wave which we are going, or the resultant wave which we are going to see because of the superposition of these two individual waves. Now, according to the principle, a field that is arising from a number of sources is determined by adding the individual fields from each source. So when you have not just two sources, you may have many sources which are sending out waves, and all of them arrive at a point simultaneously. Then the resultant will be the vector sum of all these fields. So an electric field arising from several sources is also determined by superposition of the fields from each of these sources. So this principle of superposition has got lot of applications. So one such application we see is in the electric field. So if you want to know the electric field at a point P, so it is the sum of the electric fields due to Q1 and Q2. Suppose you have a charge Q1 due to which you have an electric field. You also have a charge Q2 due to which also there is an electric field. Electric field is nothing but the space surrounding this charge where the influence of this charge is felt. So at a point P, the influence of both the charges are there, means the effect of both the fields are there. So the field at P will always be the sum, vector sum of the two fields Q1 and Q2. So studies of electric fields over an extremely wide range of magnitudes have established the validity of superposition principle. When we have done experiments with a large number of electric fields, the superposition principle has got its validity. Now coming to interference. After the principle of superposition, we are going to discuss about interference. When two waves of the same frequency and having constant phase difference. So these terms are very important. Same frequency and constant phase difference moving in the same direction, superimpose on each other, interference takes place. So now we have already seen the principle of superposition where two waves are arriving at the same point at the same time and they superimpose on each other. The resultant displacement is the vector sum of the displacements. Now here we are talking about waves having the same frequency. When I say frequency, the number of waves per unit time is called the frequency, crossing a point per unit time. You call it as frequency. And having a constant phase difference, phase always represents the state of vibration of the particle. Phase represents the state of vibration of the particle. So the two waves that we are talking about should have a constant phase difference and they should be moving in the same direction, and then they'll have to superimpose, then you will get interference pattern. Okay, so when we are talking about waves of same frequency, here I'll give you an example. This is one wave. So this is also another wave. We have another wave. So in this particular limit, this is one wavelength, length. So how many waves do we have here? Two waves. This is another one. So here also two. So in these two cases, the frequency is the same. Suppose in the other case, I have a wave like this. Now the frequency of 1 and 2 is the same, but 3 is different. So that is what we mean by frequency. And then when it comes to constant phase difference, they have the same phase here. So when I'm talking about a particle which is vibrating in the upward direction, this is the crest. And for the second also, this is the crest. So they are having the same phase. And if you see here, there is a difference in phase because the frequency is varying. So when they superimpose, you get interference. Here we have the example. If two waves occupy the same phase, their amplitudes add at each point. They may either interfere constructively or destructively. We are going to see two types here, constructive interference and destructive interference. So now we see the first case, A. So this is the first wave and this is the second wave. Obviously, if you see, the frequency is the same. The direction of propagation is the same. They are moving in the same direction. Now, when they superimpose on each other, you are getting the resultant wave. And if you see, this is the amplitude of this wave, I say A1. And this is the amplitude of this wave A2. So, the resultant amplitude will be A, which will be the sum of the amplitudes of the two waves. They are in the same direction. That is what we are trying to understand. Crest falls on crest. That means they are in the same phase. They have the same frequency. They are moving in the same direction. So we have A is equal to A1 plus A2. So what happens if two waves occupy the same space? Their amplitudes add at each point. At a particular point we take, so their amplitudes will add. Now let us see the second case. In the second case, what we are trying to see here is, if at all there is a difference in phase and it is differing, constant phase difference by wavelength lambda, then also what happens? You have the crest falling on crest. So again, the resultant displacement is the sum of the two displacement. There is a constant phase difference of lambda here. So here corresponding to lambda. So again they will add. Now, in the third case, if you see, if this is the first wave, this represents the first wave. And now this is the second wave, where you see when there is a crest here, you are getting a crest after lambda by 2. Means there is a difference of phase between the two waves. So, whenever there is a crest, there is a trough. When here there is a trough, there is a crest. So what we understand here is these two waves are differing by a wavelength lambda by 2. So when such waves interfere with each other, so if the displacement of this is A and the displacement of this is minus A because it is in the opposite direction, now the resultant displacement will be A minus A is equal to 0. So the resultant is this. So that is what we try to understand when we say the amplitudes simply add at each point. Now coming to constructive interference, it occurs at a point where two overlapping or intersecting waves of the same frequency are in phase. So in constructive interference, it occurs at a point where two overlapping or intersecting waves of the same frequency are in phase. In phase here means we have crests and troughs of the two waves coinciding with each other. So in the previous example, we have seen when a crest falls on a crest and a trough falls on a trough, then we say that they are in phase. And so then we call it as constructive interference. So in this case, what happens? The two waves reinforce with each other and combine to form a wave. And the resultant wave is the sum of the individual amplitudes of the two waves. So what we try to understand in constructive interference here is when the two waves arriving at a point having the same frequency, same amplitude and in the same phase, and they are in the same phase, they interfere or reinforce with each other so that the resultant is the sum of the amplitudes of the two waves, and then you will have the constructive interference. Now coming to destructive interference. Destructive interference occurs when the two waves of the same frequency are completely out of phase. When we say completely out of phase means the crest of one wave falls on the trough of the other. If you have to visualize how they fall out of phase means the crest of one wave will fall on the trough of the other wave, and then the two waves will cancel each other. We have seen the example now. Now if this is one wave, the crest, this is the crest and this is the trough. Now we consider the second wave. So this is the trough and this is the crest. Now if these two waves arrive at a point simultaneously because the crest coincides with the trough, so the resultant displacement will be zero because they cancel each other. So because they're cancelling, we are calling it as destructive interference. So in constructive interference, what we see here is the amplitude of the resultant wave is greater than that of either of the individual waves. And in destructive interference, the amplitude of the resultant wave is less than that of either of the waves. Let me explain this point with the help of an example. Suppose we take the first wave y1 whose amplitude is 5 centimeters. And the second wave whose amplitude is 4 centimeter. So what we are talking about in constructive interference, the resultant is the sum of the displacements of the two waves. That is the vector sum of the two displacements. Both are in the same direction. So we'll have it as 5 plus 4 is equal to 9. So what this statement means is the amplitude of the resultant wave. So why here is the amplitude of the resultant wave? This amplitude is larger or greater than any of the two. One is 5, the other is 4. But what is the resultant we are getting is 9. So the resultant is always greater than either of the displacements of the two waves. Now coming to destructive interference. Suppose we are taking the same, but they are coming in opposite, means the crest falls on a trough, means we will take y2 to be equal to minus 4 centimeter. So when we take the vector displacement, vector sum of the two displacements, y is equal to y1 plus y2, y minus 4 is equal to 1. So what this represents is 1 is small. It is less than either 5 or 4. So what here they are telling, it is less than either of the individual waves. That is what we are trying to understand. So what happens in constructive interference? We are getting waves of larger amplitude when compared to these two waves. And in destructive, it is less than either of the waves. So all interference associated with the light waves arises when electromagnetic fields that constitute the individual waves combine. So this is how we see the application of this interference phenomena. Now let us try to understand the patterns, interference patterns. So we are going to see the first pattern. So to understand this pattern, what we see here is, we are considering two slits, two sources from which two waves are coming. S1 and S2 are two sources of light. You imagine sending out waves. Okay. And this is a screen. This is the screen. Now what we are trying to understand is, two waves travel the same distance. Now we have a source here, so sending out waves. So this is the wave that is coming from source 1 and it is reaching the point O. This is the point O it is reaching. Now this is the wave coming from source 2. So this is traveling like this and reaching the point O. Now if you see the figure, you can clearly understand that both the waves are traveling equal distances. The wave that is coming from S1 and the wave coming from S2, both of them are traveling the same distance and they arrive at the point O in phase. In phase here means what? These are two coherent sources. So here you have a crest, here also a crest. So here also you have a crest, here also you have a crest. So they are in phase. The crest of one wave falls on the crest of the other wave, means they are in phase. So as a result, what we have, there will be a constructive interference. And whenever we have constructive interference, you will see a bright fringe here. So this will be a bright fringe. Slowly we are going to shift from interference and understand the fringe pattern. So constructive interference occurs at the point O when the waves combine, because they are coming in phase. So whenever you see the screen, at this point you will be observing a very bright fringe. Now let us understand pattern 2. So in pattern 2, again we have the same setup. Two sources, S1 and S2, sending out waves. And this is the screen. And this is the point P at which the waves are arriving. So this is the wave coming from the source S1 and reaching the point P. There is another wave coming from S2 and reaching the point P. Now if you see, the distance traveled by these two waves is not the same. This wave, when you compare the two waves, the wave that is coming from S2 is traveling a larger distance when compared to the wave coming from S1. So the lower wave travels one wavelength farther. So one wavelength farther means exactly one complete wave. This is one wavelength. One crest and one trough forms one complete wave that gives us one wavelength. So one wavelength farther. Because the difference is one complete wavelength, they are still in phase. So that is what we try to understand. So these two are again in phase. So what happens here again, there will be a bright fringe formed. Even though the distances are different, but they are arriving here in phase, means the crest of one wave falls on the crest of the other. So to explain here, what I can say is, this is the first wave which is arriving at this point. And if I talk about another wave which is coming from here, so this has already traveled this much distance when it comes here. But if you see these two waves, they are in phase. So this is traveling 2 lambda, but this is only lambda. But the difference is lambda, one wavelength. So therefore the crest falls on the crest and the trough falls on the trough. So they are in phase. Because they are in phase, there is constructive interference. And because of the constructive interference, there is a bright fringe. So a second bright fringe occurs at this position. Already we have a bright fringe here. So there is one more bright fringe at this point P. Now we see the pattern 3. In pattern 3, the lower wave travels 1/2 length farther than the upper wave to reach the point R. We are taking another point R. Now if you see here, these are the sources which are sending out waves. This is the screen and this is the wave coming from S1 and reaching the point R. This is the point it reaches. Now this is the second wave that is reaching this point R. Now if you see at this point when they arrive, this is the crest of the first wave and this is the trough of the second wave. So the crest falls on the trough, means they are opposite in phase. So what is happening here? There is destructive interference and you get a dark fringe. So what we try to understand here is, if this is the first wave and if you see the second wave has started here and it is going like this, means this is the crest, this is the trough. Then what happens? There is a difference in wavelength. If you consider this is lambda, so this is half the wavelength, that is lambda by 2. So they are differing in wavelength, half the wavelength. That is why we say 1/2 of the wavelength difference. So because of that, what happens? There is destructive interference. Destructive interference occurs at the point R when the two waves combine, because the lower wave falls 1/2 wavelength behind the upper wave. Now let us see the conditions for interference. First condition is the sources must be coherent. Coherent always talks about constant phase. So they must maintain a constant phase difference. The state of vibrations of the particle should be constant. So that is what we are trying to understand. The two sources that we are considering, S1 and S2, they should be coherent sources. And the two sources also should be monochromatic. Mono means always single. Chromatic is representing the color. So light of single color will have a single wavelength. So they should be in phase and also they should have a single wavelength. Then the separation between the two sources must be very small. So we are going to see the setup like this. This is the source S1. This is the source S2. And you have a screen. So these two sources S1 and S2 must be coherent. And they should always emit light of a single wavelength. And the separation between these two sources, which we call it as small d, it should be very small. They should be very near. Only then what will happen is when they arrive at a point, then you will have a constant phase difference. Then the distance between the two sources and the screen must be large. So this is what we call as capital D. Capital D is the distance between the source and the screen is capital D. Capital D should be very large. D is much greater than small d. This is the condition that is required for interference. Then the amplitude of the waves must be equal. Amplitude of the waves means we are talking about y is equal to y1 plus y2 displacements. So for both the waves, the amplitudes must be equal. If they are not equal, what happens is when they are interfering destructively, so the first one will not cancel the other one and you will not have an exactly dark fringe. You will have bright fringes followed by less bright fringes because the displacements do not cancel out and you do not get a perfect dark fringe. So the amplitude of the light waves must be equal and the two sources must be narrow. We have already seen whenever we are talking about these sources, the sources have to be very narrow so that they send out spherical waves. Then the two sources must emit lights of same wavelength and frequency. So this is also one condition we have seen for interference. For interference to occur, the two waves must have the same frequency and same wavelength. Then to view the fringes, the background must be dark. So whenever we are talking about you have a bright fringe here followed by dark fringe, bright fringe and so on. Alternate bright and dark fringes you have. But if you have to see these fringes clearly, you should have a dark background. Now coming to the types of interference. So when it comes to the types of interference, we can get interference in the first way is by division of wavefront. So the wavefront can be divided into two or more parts by the use of mirrors. So when you are using a mirror, when light falls or on a mirror, what happens? It reflects. So coherent sources can be obtained by dividing the wavefront from originating from a common source by employing the mirrors, biprisms or lenses because we want coherent sources. So instead of taking two sources, what we can do is we will take one source and allow it to fall on a mirror and take the reflected light. So when these two will interfere, we call it as division by division of wavefront. The example we see here is a Fresnel biprism. This is a perfect example for division of wavefront. And the second thing we see here is the division of amplitude. When the amplitude gets divided. So the amplitude of the incident wave can be divided into two or more parts by partial reflection and refraction. So partially it reflects and partially refracts. So coherent beams can be produced by division of amplitude. So if you want coherent beams, instead of taking two sources, you can also divide a single wavefront by the division of amplitude. Now beams travel different paths and they are finally brought together to produce interference. So what we are seeing in interference is two different beams that are interfering with each other coming in two different paths. And when they are coming in phase, we are calling it as constructive interference. And when they are coming in out of phase, we are calling it as destructive interference. So the best examples for division of amplitude is the Michelson interferometer and the Fabry-Perot's interferometer. So thank you and see you again. For more details, you can refer to P.K. Palaniswamy, Engineering Physics. See you again in the next lecture.
Like, share and subscribe. Hit the bell icon for more updates.